Observable universe. The observable universe is a ball-shaped region of the universe consisting of all matter that can be observed from Earth or its space-based telescopes and exploratory probes at the present time. The electromagnetic radiation from these objects has had time to reach the solar system and Earth since the beginning of the cosmological expansion. Initially, it was estimated that there may be 2 trillion galaxies in the observable universe. That number was reduced in 2021 to several hundred billion based on data from New Horizons. Assuming the universe is isotropic, the distance to the edge of the observable universe is roughly the same in every direction. That is, the observable universe is a spherical region centered on the observer. Every location in the universe has its own observable universe, which may or may not overlap with the one centered on Earth. The word observable in this sense does not refer to the capability of modern technology to detect light or other information from an object, or whether there is anything to be detected. It refers to the physical limit created by the speed of light itself. No signal can travel faster than light, hence there is a maximum distance, called the particle horizon, beyond which nothing can be detected, as the signals could not have reached us yet. Sometimes astrophysicists distinguish between the observable universe and the visible universe. The former includes signals since the end of the inflationary epoch, while the latter includes only signals emitted since recombination. According to calculations, the current moving distance to particles from which the cosmic microwave background radiation, CMBR, was emitted, which represents the radius of the visible universe, is about 14.0 billion parsecs, about 45.7 billion light-years. The moving distance to the edge of the observable universe is about 14.3 billion parsecs, about 46.6 billion light-years, about 2% larger. The radius of the observable universe is therefore estimated to be about 46.5 billion light-years. Using the critical density and the diameter of the observable universe, the total mass of ordinary matter in the universe can be calculated to be about 1.5 times 1053 kilograms. In November 2018, astronomers reported that extragalactic background light, EBL, amounted to 4 times 1084 photons. As the universe's expansion is accelerating, all currently observable objects, outside the local supercluster, will eventually appear to freeze in time, while emitting progressively redder and fainter light. For instance, objects with the current redshift Z from 5 to 10 will only be observable up to an age of 4 to 6 billion years. In addition, light emitted by objects currently situated beyond a certain moving distance, currently about 19 billion parsecs, will never reach Earth. Overview. The universe's size is unknown, and it may be infinite in extent. Some parts of the universe are too far away for the light emitted since the Big Bang to have had enough time to reach Earth or space-based instruments, and therefore lie outside the observable universe. In the future, light from distant galaxies will have had more time to travel, so one might expect that additional regions will become observable. Regions distant from observers, such as us, are expanding away faster than the speed of light, at rates estimated by Hubble's law. The expansion rate appears to be accelerating, which dark energy was proposed to explain. Assuming dark energy remains constant, an unchanging cosmological constant, so that the expansion rate of the universe continues to accelerate, there is a future visibility limit beyond which objects will never enter the observable universe at any time in the future because light emitted by objects outside that limit could never reach the Earth. Note that, because the Hubble parameter is decreasing with time, there can be cases where a galaxy that is receding from Earth only slightly faster than light emits a signal that eventually reaches Earth. This future visibility limit is calculated at a moving distance of 19 billion parsecs, 62 billion light-years, assuming the universe will keep expanding forever, which implies the number of galaxies that can ever be theoretically observed in the infinite future is only larger than the number currently observable by a factor of 2.36, ignoring redshift effects. In principle, more galaxies will become observable in the future. In practice, an increasing number of galaxies will become extremely redshifted due to ongoing expansion, so much so that they will seem to disappear from view and become invisible. A galaxy at a given moving distance is defined to lie within the observable universe if we can receive signals emitted by the galaxy at any age in its history, say, a signal sent from the galaxy only 500 million years after the Big Bang. Because of the universe's expansion, there may be some later age at which a signal sent from the same galaxy can never reach the Earth at any point in the infinite future. So, for example, we might never see what the galaxy looked like 10 billion years after the Big Bang, even though it remains at the same moving distance less than that of the observable universe. This can be used to define a type of cosmic event horizon whose distance from the Earth changes over time. For example, the current distance to this horizon is about 16 billion light-years, meaning that a signal from an event happening at present can eventually reach the Earth if the event is less than 16 billion light-years away, but the signal will never reach the Earth if the event is further away. The space before this cosmic event horizon can be called reachable universe, that is, all galaxies closer than that could be reached if we left for them today, at the speed of light. All galaxies beyond that are unreachable. Simple observation will show the future visibility limit, 62 billion light-years, is exactly equal to the reachable limit, 16 billion light-years, added to the current visibility limit, 46 billion light-years. The universe versus the observable universe. Both popular and professional research articles in cosmology often use the term universe to mean observable universe. This can be justified on the grounds that we can never know anything by direct observation about any part of the universe that is causally disconnected from the Earth, although many credible theories require a total universe much larger than the observable universe. No evidence exists to suggest that the boundary of the observable universe constitutes a boundary on the universe as a whole, nor do any of the mainstream cosmological models propose that the universe has any physical boundary in the first place. However, some models propose it could be finite but unbounded, like a higher dimensional analog of the 2D surface of a sphere that is finite in area but has no edge. It is plausible that the galaxies within the observable universe represent only a minuscule fraction of the galaxies in the universe. According to the theory of cosmic inflation initially introduced by Alan Guth and D. Kazanas, if it is assumed that inflation began about 10⁻37 seconds after the Big Bang and that the pre-inflation size of the universe was approximately equal to the speed of light times its age, that would suggest that at present the entire universe's size is at least 1.5 times 1034 light-years. At least 3 times 1023 times the radius of the observable universe. If the universe is finite but unbounded, it is also possible that the universe is smaller than the observable universe. In this case, what we take to be very distant galaxies may actually be duplicate images of nearby galaxies, formed by light that has circumnavigated the universe. It is difficult to test this hypothesis experimentally because different images of a galaxy would show different eras in its history, and consequently might appear quite different. Aloud et al. Claimed to establish a lower bound of 27.9 gigaparsecs, 91 billion light-years, on the diameter of the last scattering surface. This value is based on matching circle analysis of the WMAP 7-year data. This approach has been disputed. Size. The moving distance from Earth to the edge of the observable universe is about 14.26 gigaparsecs, 46.5 billion light-years or 4.40 times 1026 meters, in any direction. The observable universe is thus a sphere with a diameter of about 28.5 gigaparsecs, 93 billion light-years or 8.8 times 1026 meters. Assuming that space is roughly flat, in the sense of being a Euclidean space, this size corresponds to a moving volume of about 1.22 times 104 GPC3, 4.22 times 105 Gly3 or 3.57 times 1080 cubic meters. These are distances now, in cosmological time, not distances at the time the light was emitted. For example, the cosmic microwave background radiation that we see right now was emitted at the time of photon decoupling, estimated to have occurred about 380,000 years after the Big Bang, which occurred around 13.8 billion years ago. This radiation was emitted by matter that has, in the intervening time, mostly condensed into galaxies, and those galaxies are now calculated to be about 46 billion light-years from Earth. To estimate the distance to that matter at the time the light was emitted, we may first note that according to the Friedmann-Lemaitre-Robertson-Walker metric, which is used to model the expanding universe, if we receive light with a redshift of z, then the scale factor at the time the light was originally emitted is given by a t equals 1 plus z. WMAP 9-year results combined with other measurements give the redshift of photon decoupling as z equals 1091.64 plus minus 0.47, which implies that the scale factor at the time of photon decoupling would be 1092.64. So if the matter that originally emitted the oldest CMBR photons has a present distance of 46 billion light-years, then the distance would have been only about 42 million light-years at the time of decoupling. The light travel distance to the edge of the observable universe is the age of the universe times the speed of light, 13.8 billion light-years. This is the distance that a photon emitted shortly after the Big Bang, such as one from the cosmic microwave background, has traveled to reach observers on Earth. Because space-time is curved, corresponding to the expansion of space, this distance does not correspond to the true distance at any moment in time. Matter and mass. Number of galaxies and stars. The observable universe contains as many as an estimated 2 trillion galaxies and, overall, as many as an estimated 1,024 stars, more stars, and, potentially, Earth-like planets, than all the grains of beach sand on planet Earth. As mentioned earlier, the estimated number of galaxies was reduced in 2021 to several hundred billion based on data from New Horizons. The estimated total number of stars in an inflationary universe, observed and unobserved, is 10,100. Matter content, number of atoms. Assuming the mass of ordinary matter is about 1.45 times 1053 kilograms as discussed above, and assuming all atoms are hydrogen atoms, which are about 74% of all atoms in the Milky Way by mass, the estimated total number of atoms in the observable universe is obtained by dividing the mass of ordinary matter by the mass of a hydrogen atom. The result is approximately 1080 hydrogen atoms, also known as the Eddington number. Mass of ordinary matter. The mass of the observable universe is often quoted as 1053 kilograms. In this context, mass refers to ordinary, baryonic, matter and includes the interstellar medium, ISM, and the intergalactic medium, IGM. However, it excludes dark matter and dark energy. This quoted value for the mass of ordinary matter in the universe can be estimated based on critical density. The calculations are for the observable universe only as the volume of the whole is unknown and may be infinite. Estimates based on critical density. Critical density is the energy density for which the universe is flat. If there is no dark energy, it is also the density for which the expansion of the universe is poised between continued expansion and collapse. From the Friedmann equations, the value for ρ c critical density is where g is the gravitational constant and h equals h0 is the present value of the Hubble constant. The value for h0, as given by the European Space Agency's Planck telescope, is h0 equals 67.15 km per second per megaparsec. This gives a critical density of 0.85 times 10⁻26 kg/m3, or about 5 hydrogen atoms per cubic meter. This density includes 4 significant types of energy/mass: ordinary matter, 4.8%, neutrinos, 0.1%, cold dark matter, 26.8%, and dark energy, 68.3%. Although neutrinos are standard model particles, they are listed separately because they are ultra-relativistic and hence behave like radiation rather than like matter. The density of ordinary matter, as measured by Planck, is 4.8% of the total critical density, or 4.08 times 10⁻28 kg/m3. To convert this density to mass we must multiply by volume, a value based on the radius of the observable universe. Since the universe has been expanding for 13.8 billion years, the moving distance, radius, is now about 46.6 billion light-years. Thus, volume 4/3 pi r3 equals 3.58 times 1080 cubic meters, and the mass of ordinary matter equals density 4.08 times 10⁻28 kg/m3 times volume 3.58 times 1080 cubic meters, or 1.46 times 1053 kilograms. Large-scale structure. Sky surveys and mappings of the various wavelength bands of electromagnetic radiation, in particular 21 cm emission, have yielded much information on the content and character of the universe's structure. The organization of structure appears to follow a hierarchical model, with organization up to the scale of superclusters and filaments. Larger than this, at scales between 30 and 200 megaparsecs, there seems to be no continued structure, a phenomenon that has been referred to as the end of greatness. Walls, filaments, nodes, and voids. The organization of structure arguably begins at the stellar level, though most cosmologists rarely address astrophysics on that scale. Stars are organized into galaxies, which in turn form galaxy groups, galaxy clusters, superclusters, sheets, walls and filaments, which are separated by immense voids, creating a vast foam-like structure sometimes called the cosmic web. Prior to 1989, it was commonly assumed that virialized galaxy clusters were the largest structures in existence, and that they were distributed more or less uniformly throughout the universe in every direction. However, since the early 1980s, more and more structures have been discovered. In 1983, Adrian Webster identified the Webster LQG, a large quasar group consisting of 5 quasars. The discovery was the first identification of a large-scale structure, and has expanded the information about the known grouping of matter in the universe. In 1987, Robert Brent Tully identified the Pisces-Cetus supercluster complex, the galaxy filament in which the Milky Way resides. It is about 1 billion light-years across. That same year, an unusually large region with a much lower than average distribution of galaxies was discovered, the Giant Void, which measures 1.3 billion light-years across. Based on redshift survey data, in 1989 Margaret Geller and John Hooker discovered the Great Wall, a sheet of galaxies more than 500 million light-years long and 200 million light-years wide, but only 15 million light-years thick. The existence of this structure escaped notice for so long because it requires locating the position of galaxies in 3 dimensions, which involves combining location information about the galaxies with distance information from redshifts. 2 years later, astronomers Roger G. Close and Louis C. Campuzano discovered the Close-Campuzano LQG, a large quasar group measuring 2 billion light-years at its widest point, which was the largest known structure in the universe at the time of its announcement. In April 2003, another large-scale structure was discovered, the Sloan Great Wall. In August 2007, a possible supervoid was detected in the constellation Eridanus. It coincides with the Cymbe cold spot, a cold region in the microwave sky that is highly improbable under the currently favored cosmological model. This supervoid could cause the cold spot, but to do so it would have to be improbably big, possibly a billion light-years across, almost as big as the giant void mentioned above. Another large-scale structure is the SSA-22 protocluster, a collection of galaxies and enormous gas bubbles that measures about 200 million light-years across. In 2011, a large quasar group was discovered, U1.11, measuring about 2.5 billion light-years across. On January 11, 2013, another large quasar group, the huge LQG, was discovered, which was measured to be 4 billion light-years across, the largest known structure in the universe at that time. In November 2013, astronomers discovered the Hercules Corona Borealis Great Wall, an even bigger structure twice as large as the former. It was defined by the mapping of gamma-ray bursts. In 2021, the American Astronomical Society announced the detection of the giant arc, a crescent-shaped string of galaxies that span 3.3 billion light-years in length, located 9.2 billion light-years from Earth in the constellation Boötes from observations captured by the Sloan Digital Sky Survey. End of Greatness. The end of greatness is an observational scale discovered at roughly 100 mpc, roughly 300 million light-years, where the lumpiness seen in the large-scale structure of the universe is homogenized and isotropized in accordance with the cosmological principle. At this scale, no pseudorandom fractalness is apparent. The superclusters and filaments seen in smaller surveys are randomized to the extent that the smooth distribution of the universe is visually apparent. It was not until the redshift surveys of the 1990s were completed that this scale could accurately be observed. Observations. Another indicator of large-scale structure is the Lyman alpha forest. This is a collection of absorption lines that appear in the spectra of light from quasars, which are interpreted as indicating the existence of huge thin sheets of intergalactic, mostly hydrogen, gas. These sheets appear to collapse into filaments, which can feed galaxies as they grow, where filaments either cross or are dense. An early direct evidence for this cosmic web of gas was the 2019 detection, by astronomers from the Riken Cluster for Pioneering Research in Japan and Durham University in the UK, of light from the brightest part of this web, surrounding and illuminated by a cluster of forming galaxies, acting as cosmic flashlights for intercluster medium hydrogen fluorescence via Lyman alpha emissions. In 2021, an international team, headed by Roland Bacon from the Centre de Recherche Astrophysique de Lyon, France, reported the first observation of diffuse extended Lyman alpha emission from redshift 3.1 to 4.5 that traced several cosmic web filaments on scales of 2.5-4 cmpc, moving megaparsecs, in filamentary environments outside massive structures typical of web nodes. Some caution is required in describing structures on a cosmic scale because they are often different from how they appear. Gravitational lensing can make an image appear to originate in a different direction from its real source, when foreground objects curve surrounding space-time, as predicted by general relativity, and deflect passing light rays. Rather usefully, strong gravitational lensing can sometimes magnify distant galaxies, making them easier to detect. Weak lensing by the intervening universe in general also subtly changes the observed large-scale structure. The large-scale structure of the universe also looks different if only redshift is used to measure distances to galaxies. For example, galaxies behind a galaxy cluster are attracted to it and fall towards it, and so are blue-shifted, compared to how they would be if there were no cluster. On the near side, objects are redshifted. Thus, the environment of the cluster looks somewhat pinched if using redshifts to measure distance. The opposite effect is observed on galaxies already within a cluster. The galaxies have some random motion around the cluster center, and when these random motions are converted to redshifts, the cluster appears elongated. This creates a finger of God, the illusion of a long chain of galaxies pointed at Earth. Cosmography of Earth's cosmic neighborhood. At the center of the Hydra Centaurus supercluster, a gravitational anomaly called the Great Attractor affects the motion of galaxies over a region hundreds of millions of light-years across. These galaxies are all redshifted, in accordance with Hubble's law. This indicates that they are receding from us and from each other, but the variations in their redshift are sufficient to reveal the existence of a concentration of mass equivalent to tens of thousands of galaxies. The Great Attractor, discovered in 1986, lies at a distance of between 150 million and 250 million light-years in the direction of the Hydra and Centaurus constellations. In its vicinity there is a preponderance of large old galaxies, many of which are colliding with their neighbors, or radiating large amounts of radio waves. In 1987, astronomer R. Brent Tully of the University of Hawaii's Institute of Astronomy identified what he called the Pisces-Cetus supercluster complex, a structure 1 billion light-years long and 150 million light-years across, in which, he claimed, the local supercluster is embedded. Most distant objects. The most distant astronomical object identified as of August of 2024, is a galaxy classified as JADES GZ140. In 2009, a gamma-ray burst, GRB 090423, was found to have a redshift of 8.2, which indicates that the collapsing star that caused it exploded when the universe was only 630 million years old. The burst happened approximately 13 billion years ago, so a distance of about 13 billion light-years was widely quoted in the media, or sometimes a more precise figure of 13.035 billion light-years. This would be the light-traveled distance, see distance measures, cosmology, rather than the proper distance used in both Hubble's law and in defining the size of the observable universe. Cosmologist Ned Wright argues against using this measure. The proper distance for a redshift of 8.2 would be about 9.2 GPC, or about 30 billion light-years. Horizons. The limit of observability in the universe is set by cosmological horizons, which limit, based on various physical constraints, the extent to which information can be obtained about various events in the universe. The most famous horizon is the particle horizon, which sets a limit on the precise distance that can be seen due to the finite age of the universe. Additional horizons are associated with the possible future extent of observations, larger than the particle horizon owing to the expansion of space, an optical horizon at the surface of last scattering, and associated horizons with the surface of last scattering for neutrinos and gravitational waves.